Yes, Shubhabrata, you can start your lecture. Shubhabrata, can you hear me? We can't hear you.
Oh, okay. Sorry. Yeah, I was still muted. Sorry. Thank you. Okay. So in geometric small cancellation, we saw under what condition this theorem states that under what conditions this family, which we call the moving family, will give us these normal subgroups as free groups. I mean, not free groups, sorry, a free product of some families, subfamilies, and also the quotient as a hyperbolic group. So now we will move on to another small cancellation condition, another notion where small cancellation was extended. This was done by Gromov, and this was done in his famous article called Random Walks in Random Groups. There he introduced this method primarily to construct a group which some people call Gromov's monster, and that is a group like this. I mean, that group Gromov constructed in that article is like a limit, such a limit group. And I mean, it was done by a taking such successive quotients of hyperbolic groups in order to do something, enforcing a certain requirement that was he wanted to construct a group whose Cayley graph does not coarsely embed in a Hilbert space. So for that, what he did is he embedded something called an expander graph, which is generally described by a family of graphs. So in this construction, what Gromov did is he successively embedded graphs from this family in the Cayley graph and the limit the entire thing called the expander graph. He embedded in the Cayley graph, and resultingly that group and its Cayley graph does not coarsely embed in a Hilbert space. And that is a major result because it serves as a counterexample to something called a Baum-Kohn conjecture and some version of it. And this was for a very long time, I think, the only example of that sort. Recently, maybe 2 or 3 years back, Damian Osaida has constructed a similar example by employing closely related means. So, and that result of Gromov gave rise to a lot of research in that direction. There is a very famous article written by, expository article I would say, written by Arzantseva and Delzan, explaining the proof, main ingredients and the proof of Gromov's theorem in there. And there are other such survey articles and expository articles on Gromov's article. So this article by Arzantseva and Delzan is called Examples of Random Groups, and that is a very nicely written. So you can find all these stuff there. So what is this? What is a graphical small cancellation? What we want to see here is we start with a set S that you can consider as the set of labels, like the set of generators. And then if we consider theta k, which is so here there is a little bit confusion. Here it's written theta k, here it's written rows k. So these are the same things here. So theta k, if it's the rows of k petals, then that is a free group on these labels, these generating elements, and that is a free group on k generators, free group of rank k. Now, what Gromov did was he extended the small cancellation notion on a labeled graph. So what was it? He labeled a graph using the labels coming from S. So you take a graph theta, and you assume that it has no degree of vertex of degree 1, and suppose it is connected. You can also introduce similar things on non-connected graph, but suppose here we will assume it to be connected. So otherwise some complications would arise. We have to be more careful about the statements. So a labeling of that graph theta by that set S is just a map M from theta to rows k or theta k, whatever. Take one of them. So it is just a map from the given graph theta to rows k. What do we do? Which sends each edge in this graph to an element of S plus minus, that is the symmetrized S. Okay, so we have a graph theta. Take each edge of the graph and map it to some element of S plus minus. What does it do for us? It is giving each edge of theta a label using S elements. Okay, so sending an edge to this rows on k petals means we are giving them a label. So now if we take M star, the induced map at the level of the fundamental groups. So you see that rows k, the fundamental group of rows k would be the free group on k generators or Fs here. So we will have a mapping from this, the fundamental group of this graph, the given graph theta, pi 1 theta. So we will get a map from pi 1 theta to the pi 1 of rows k, which is Fs. So what we are getting essentially is we have a map, labeling map M to, let's call it theta k. Now M star would be a map from pi 1 theta to pi 1 theta k, and M, this is a homomorphism, and M star of pi 1 theta is a subgroup of pi 1 theta k, which is Fk. Okay, so in this way what we are getting is a subgroup of Fs, which is here, this is Fs. S is a set with k levels. So what we are getting essentially is a subgroup pi 1 theta in Fs. So this is now serving us as R. Okay. Now we have to talk about small cancellation in this context. So what would be a small how to define small cancellation? We have to first talk about piece or something similar. So here he talked about a piece, and a piece here would be this is a label graph. The image of this graph is a label graph. So each edge there you have a label. Fine. Now a label here, sorry, a piece here in the label graph is just a simple path in theta. You're not looking at the path in theta k, where the image lies. Looking at a path in theta, that path would get, via the map M, the path in theta would get a label, right? So if alpha is a path, if it's a simple path in theta, you will get a label for that via M. Now, you'll call that simple path alpha to be a piece if there is another simple path beta, subset beta is a path in theta, and if the two simple paths, if they are related by a label preserving isometry. So first thing is that they have to have the same length. If it's a path of length L, if alpha is a path of length L in theta, beta has to be also a path of length L, and the label of alpha has to be the same as label of beta. So it's a very understandable definition, quite natural. If we have to call some such path as a piece, and we will call some such path as a piece because our elements essentially are coming from this. So our relators would come from this, and relators would be like cycles, and pieces would be subpaths of those cycles. So here, what are we looking at? We are looking at m star of pi 1 theta. So pi 1 thetas are essentially loops in theta, classes of loops in theta. So they are essentially cycles. So, and when do we, so if those cycles are to serve as our relators, when do we call something a piece? When two such cycles will overlap on a common subword. So a common subword will be a simple path on those cycles, right? So that is why a piece will be such a simple path in theta. And when do we call that a piece? When it's a common subword. So that means there exists, like in the classical small cancellation definition, when did we call U to be a piece? When there exists, when U was a subword of R, and we had another relator R prime having the same word U as a prefix. So when U was a prefix of a given relator R, it is a piece if it is also a prefix of another related R prime. Similarly, here a simple path in theta is a piece if there is another simple path beta which has the same length and the same label is, I mean, when we have another simple path with the same length and same label. Fine. So that is a piece. Small cancellation condition in theta, how do we generalize that? Now CP, so CP is it's very similar to the previous CP condition that we introduced. What was that CP condition? That no relator is, so each relator is concatenation of at least p pieces, right? So no relator is a disjoint union of less than p pieces. So each one has to be at least p. It's saying the same thing. No cycle, that means no relator. No cycle in theta, that means no relator. That means no element in m star pi 1 theta. No cycle, no cycle in theta is disjoint union of fewer than p pieces. Exactly the same thing. So what is C prime lambda? Now C prime lambda for lambda in 0, 1, what was it in the classical case? That the largest piece is less than lambda times the, say, smallest relator. That was the stronger condition, and the usual C prime was the largest piece in that subword in that relator is less than lambda times the length of that relator. So here C prime lambda is length of a cycle in theta is strictly greater than 1 over lambda times length of the longest piece in the cycle, right? So what was the definition for our the classical small cancellation? Length of the longest piece in the relator length of the longest piece in the relator is less than lambda times length of the relator, right? That means length of the relator is greater than length of the relator is greater than 1 by lambda times length of the piece, longest piece, right? Exactly the same thing here is being said. Length of the relator, that is length of the cycle, is strictly greater than 1 over lambda times length of the longest piece in the cycle. So that is the C prime lambda small cancellation condition that was introduced by Gromov. It's called the graphical small cancellation condition. This is a metric one, and this is the combinatorial one. So let theta be a finite connected graph. So this is the small cancellation theorem. So let theta be a finite connected graph and M be a reduced C7 labeling of theta. So M, you recall that M was a map from theta to the rows that was giving the labeling. So what we take here is theta is a finite connected graph and M be a labeling, which is a C7 labeling. That is following this, that no cycle is a disjoint union of less than 7 pieces. At least 7 pieces you have in all of the cycles that are there in theta. Okay, so essentially what you are saying is in your relators, those are there in m star of pi 1 theta, which are like the cycles. They are, all of them, they are concatenation of at least 7 pieces. Okay, so that is somewhat similar to the C prime 1/6 situation, right? So C prime 1/6 will imply that. So here the theorem says if theta is a finite connected graph and M be a labeling, which is C7. So here the small cancellation condition is really coming from the labeling, right? So labeling is important. So if M satisfies C7, then the corresponding quotient group that we had seen here. So the quotient group is, so for the labeling M, we are considering the quotient, which is Fs quotiented by M star of pi 1 theta, right? So that is the quotient group. Now, what this result is saying is if theta is finite connected, plus M is C7 implies Gm is hyperbolic. And also, this is important, and also theta embeds in the Cayley graph of Gm. And this is exactly how Gromov has proved by showing this, that he was able to embed that expander graph in the Cayley graph of the resulting group that he had constructed. So this is the theorem that Gromov had proven. And this theorem has been illustrated in a little more detail in Arzan Seva and Delzan's article. You can have a look at it there. Okay, so now can we see this graphical small cancellation thing in terms of these things we had talked about a few minutes back, the geometric small cancellation? Yes, and what is that? That is, if we take a presentation like this, and it is a hyperbolic group, and let us call P, let us take P to be the presentation polyhedra, and we consider the universal cover of that. And we see that G will be acting on that freely, discretely, co-compactly, and all those things. And the Cayley graph of G is just contained in the one skeleton of that. Okay, so if we take this situation, so here X is the universal cover of that presentation polyhedra, and that is a hyperbolic space, a 2 delta hyperbolic space where G is acting nicely. Very good. So, and the Cayley graph is also in a way embedded there. So what we are saying is, now if we take theta to be a finite connected graph, and it's
Can you hear me?
sorry, yes.
Yeah. So what is this polyhedra representation corresponding to the?
Just take the Cayley complex, Cayley to presentation 2 complex.
Okay, so then, yeah. For example, if I take Z cross Z, so the Cayley complex
Yes.
is torus, right?
Sorry.
If I take Z cross Z,
Yes.
community set and commutator is the relation. So
Yes.
the Cayley complex just that torus.
Yes. Yes. And you take the universal cover, you are in R2, where Z2 acts this way.
Okay, I see.
Okay.
Okay.
Shall I continue?
Yes.
Okay. So now what we do is, let theta be a finite connected graph, M be a labeling of theta by the generating elements here. And now that will induce a homomorphism from pi 1 theta to what? We are labeling it by S, so it will go to G, right? Because all these elements of theta, they are labeled by these S elements, right? So now we take the universal cover of theta, and we fix a base point on that. So that will essentially, what we are looking for is to map the universal cover of that given graph theta inside the Cayley graph of G. Okay. So we take a map, a labeling of theta by these generating elements, and we get a corresponding map from the universal cover of the finite graph theta inside the Cayley graph of G. So call the image X. Now what we do is we look at so we are essentially doing the same thing here, but not in the free group situation. We are doing it in a little more general situation. So you look at this same subgroup that we had considered earlier, and this subgroup is acting freely on Y. Why? Because G is acting freely on X, right? So we consider this situation, and now we consider these invariants. They are very similar to the invariants we have seen here. So this is like the relator length, the translation length, and this is a little stronger thing, that you look at the stable relator length, right? Stable length of G. So earlier we were looking only at G x naught the difference of g x naught and x naught, and looking at the infimum. So here we are looking at the limit of this difference, where we are looking at the powers of g and dividing it by n, looking at the distance and then dividing it by n, taking the limit. So this is called the stable length. And this is the injectivity radius. What is the injectivity radius? Earlier we saw that this is like the smallest relator length, right? So we define it the same way here. We define this gx, the stable length, and then we take the minimum for all these elements. Now the length of the largest piece, it is also defined the same way. Here it is a little more general, that instead of taking the intersection of those two, here we are taking the maximum. We remember that we are always interested in the largest length of the largest piece. So here we are taking the maximum. So maximum of what? So these are essentially our relators. Keep that in mind. These are essentially our relators. So what we are doing here is we are taking the maximum of the projections corresponding to g's coming outside of g. So we are taking the projection of gy on y. That is the length of the largest piece in this context that has been defined. And similarly, corresponding to this, we define this number to be the geometric small cancellation coefficient. See, earlier also we called this delta divided by rho as to be less than epsilon. So here it was proved by Gromov and also Arzantseva and Delza in that article, that for suitable parameters, those are involved here, there will exist a lambda naught such that for all lambda less than lambda naught, this lambda we mean here, the geometric small cancellation coefficient. If lambda is less than lambda naught, then the corresponding quotient, G quotiented by normal subgroup spanned by H, would be non-elementary torsion-free hyperbolic group. That is sort of the main theorem of both Gromov's paper, and I mean it is written in a sort of cryptic way there, but in that article by Arzantseva and Delza, it is more it's done more concretely. So we have introduced sort of a series of generalizations. All are motivated by the same classical small cancellation conditions. Mostly the metric ones, and also at times the combinatorial ones. So here we see generalization of small cancellation over hyperbolic groups in these two methods, one by Olshansky, another by Delza. Then by repeating the theorems that we get either from Olshansky or from Delza, by iterating that, we get a sequence of quotients, and we get something called a graded small cancellation structure. And then we saw geometric small cancellation, and that was kind of big scale generalization of the small cancellation ideas to a much wider context. And the theorems in all these contexts are very same to the classical small cancellation theorem. So this is a recurring theme, that if you can, like the question we started with in the very beginning, that what is the main problem, what is the main essentially the single question in this small cancellation theory. If you remember, we had mentioned this question, which recurs in all these situations, is that what is it in small cancellation theory that we are studying? So it is essentially finding conditions over, if we are given, say, subgroups R1, R2, Rn. It is essentially finding in a group G. It is essentially finding conditions over R1, R2, Rn such that the normal subgroup generated by R1, R2, Rn, this family of subgroups in G, will be reasonably behaved, will be well behaved. I mean, I'm not saying free. So it's like in this geometric small cancellation situation, we saw that it's not a free group. In Delza's result, where he had considered single elements f1, f2, fn, there he could manage to get a single index n such that if you take indices higher than that, then all of them, they will generate a free group and so on. So that's not happening always. So in more and more general context, but you are getting the themes are remaining the same. What we are getting here is we are taking the same subgroup, normal subgroup generated by R1, R2, Rn, and that is a free product of some of these Ris. Okay, so essentially the theme is remaining the same, and the quotient is hyperbolic. So that is generally what we are looking for in small cancellation theory in different contexts. So when our starting point is, I mean, we don't have a very strict, nice situation like free group on S generators and for taking relators from there. Then the defining pieces and relator lengths, all these things become a little more difficult, but we can manage it like this. This is what I wanted to uh, outline today, that these are the generalizations, and these are all of them, they are carrying the same theme that we had seen in the first two lectures, where we had shown that a classical small cancellation group will be hyperbolic if yeah, they will be hyperbolic. So yeah, I will, sorry. uh,
So, in the limit, when you're
yeah,
in the limit,
which limit?
so this G1 to G2, G2 to G2, you can construct this hydrogen, right?
Yes, yes.
So, what will be the direct limit, right? Uh,
Sorry. Yes.
you are getting direct limit, right?
Yeah.
So, that will be also a finitely generated group.
Not yeah, it will be a finitely generated group, but not always a finitely presented group. But in some cases, like in Gromov's theorem, he shows that it's a finitely presented group as well.
So,
So
so can you say something about the limit group? I mean, what property?
yeah, I will tell about the limit group. So in certain cases, they are I will talk about. Let me first talk about the other generalizations that I had planned to mention. These are, I won't be saying any mathematics, just some survey of existing results in this direction. So geometric small cancellation was done essentially by Damani, Girardel, Osin, Coulomb, and others, and many important results have been proven using these tools in mapping class groups, outfns, and so on. So also this small cancellation theory was extended to relatively hyperbolic groups by Dennis Osin. And that was done more in the line of Olshansky, generalizing the epsilon pieces and things like that, and to a more general context of relatively hyperbolic groups. And he also constructs a monster there. Some, I mean, he embeds things in a finitely generated group. I mean, so he constructs a limit of such groups in his famous Annals paper on this small cancellation of relatively hyperbolic groups, small cancellation over relatively hyperbolic groups, and some embedding theorems. That is what he proves there. He proves essentially any countable group can be embedded in a two generated group. So that is kind of very surprising, and in a way that two elements of the same order are conjugate there. Any two elements of the same order are conjugate in that bigger group. So this is a very strange result by Osin, and he employs small cancellation techniques to prove that. He essentially develops the entire theory of small cancellation over relatively hyperbolic groups, and then proves that. So that's another direction. And later, small cancellation theory was extended to some groups called some groups something admitting something called acylindrical action on hyperbolic spaces. So this is also an interesting class of groups, which includes hyperbolic groups, relatively hyperbolic groups, and and other groups like mapping class groups and out FN and such interesting groups this class includes. And small cancellation was proven to this setting also by Michael Hull, who was a student of Osin, and hence by showing small cancellation, it proves the SQ universality, that I mean having many quotients. So entirely a different direction of different direction in which small cancellation was generalized was by Danny Wise. Danny Wise had generalized the small cancellation notions for a very long time, from the early 90s, I guess, to a graphical setting, which is a little different from what we called the graphical small cancellation following Gromov. Wise's small cancellation conditions on graphs were different, but he also proved similar results in that context, which I did not go into. So he had written at least two to three papers on these graphical small cancellations, and he was trying to prove some results regarding those residual finiteness. He was trying to prove residual finiteness in that generalizations context, small cancellation for graphs. And he extended small cancellation also to cat zero cube complexes. And that was kind of major generalization, I mean, very wide generalization of small cancellations. And that was very significantly used in Wise's work for the quasi-con that I forgot that term, that hierarchies of quasi-convex hierarchies for hyperbolic groups. That big fat work by Wise, he developed the small cancellation conditions over cat zero cube complexes and proved many important results using those. Anyway, so this is just a quick survey of the existing. There are, of course, other results by many other people along these lines. So a few examples of application. One we saw is dense algorithm and decision problems for this class of groups. Den filling in relatively hyperbolic groups, which is something like this, which was done by Osin and also I think Groves and Manning, and also by Damani, Giradil and Osin in terms of geometric small cancellation. So that is a major application. And the normal subgroup structures in the free groups, hyperbolic, relatively hyperbolic groups, mapping class groups, out FNs. So since we have these general version of small cancellation theory and all the subsequent ones, so we can understand the normal subgroup structures better in all these groups. And SQ universality, that is, getting given groups as quotients of groups from these classes. So, and Rip's theorem is one major development which gives many examples in this context using small cancellation constructions. And finally, constructing monsters in the sense these monster groups. I mean, they're called monsters because of their crazy properties, and these constructions were made using small cancellation theory. So that is all I plan to talk about. And Obijita, you asked about the graded small cancellation things, right? This one.
Yes, right.
Yeah, so these groups are not necessarily, the limit groups are not necessarily hyperbolic. In certain situations they are, but not necessarily always. But and they are. I mean, there are examples of the limit being not even relatively hyperbolic. So the limits vary quite a lot, and these limits are called. They have a name. They belong to a class called lacunary hyperbolic groups, and the lacunary hyperbolic groups were studied by Olshansky, Osin, and Sapir. And lacunary hyperbolic groups are those which are defined in terms of their asymptotic cones. Like we know that Gromov hyperbolic groups can be characterized through their asymptotic cones, asymptotic cones being are trees always, real trees. And these are groups, these lacunary hyperbolic groups are those which will have at least one asymptotic cone to be an R tree. So, and this is a result by Olshansky, Osin, and Sapir that groups obtained like this, the graded small cancellation groups, they are lacunary hyperbolic. Not only they are lacunary hyperbolic, they have a very nice structure of the asymptotic cones, of their asymptotic cones. Their asymptotic cones can be either a real tree or a circle tree. What I mean by a circle tree is, say, trees made out of circles. I mean, you replace edges by circles, something like that. So this is proven by Olshansky, Osin, and Sapir. And Drutu and Sapir has this characterization of relatively hyperbolic groups in terms of tree graded spaces. So these circle trees are tree graded spaces, definitely, but this also shows a limiting situation in the sense that not all tree graded, groups with asymptotic cones as tree graded spaces are not always relatively hyperbolic. So there are examples of graded small cancellation groups whose asymptotic cones are tree graded spaces, but they are not relatively hyperbolic. And yeah, all these Gromov monster, Olshansky monster, and Osin's monster. So all these things are graded small cancellation groups. The most famous being the Gromov's monster, which serves as a counterexample to this uh, Baum-Kohn conjecture, the version of Baum-Kohn conjecture. So yes, any other question? And thank you for attending. So any other question? Okay, thank you. So shall I stop sharing?
Yeah, we can stop the sharing. Thank you very much for giving a pleasant talk.
Thank you.
Yeah, shall we
Okay.
stop recording? Any question?
Okay, Abhijita. So nice
So I think
talking here.
during this
Okay.
talks,
Okay. Thank you. So I'll leave. No.
yes, I'm ending the meeting.
Okay. Thank you.